In the last video, we looked at how two events can share probability, i.e. mutual exclusivity. But consider that this did not speak to the hierarchy of influence that events can or cannot have on each other, but rather only if they shared probabilistic space. A clear example of this would be if I were to draw a king from two separate decks of cards. Drawing a king from the first deck is going to have nothing to do with the probability of my drawing a king from this second deck. So the probability compounds, and we are simply left with the formula probability of A and B is equal to the probability of A times the probability of B. So with regards to the two decks, two kings problem, you can have two possible outcomes. The first is that you draw a king, which would be about 7.6%, and the other would be the far more likely event that you would not draw a king, and that's about 92.3%. So this is one event. So separate from this is another, and its likelihood is the exact same. Now, being independent, the probability that either one of these events will occur does not change from deck to deck, and the order does not change these. So when these begin branching off of each other, the king, no king, whatever way I tack this bottom one up here after following this event, or however I put it right here after this event, the probabilities that I should draw a king or not a king each time do not change, but rather simply compound in time through this multiplication principle. So 7.6 times 7.6% would be the probability of getting a king, then a king. 7.6 times 92.3% would be the probability of you getting a king, then not a king. Now, consider we are drawing two kings from the same deck. And we've already shown that the probability of either one of these two decks of cards occurring, their fair decks, are equal. But considering that one has to occur before the other, removing a card, whether it is a king or not, will change the probability of drawing a king on the second time around. For example, how your probability will change depends on the card you removed. So if you draw a king your first time with a 7.6% chance, the next time around you'll have one less king and one less card. Consider that you draw a king the first time around, and then the second time you don't. You still have one less card, but not one less king. So there's this seesaw effect where the removal of the first king will change the probability that the second one will be drawn. This means that the two events are not independent. Because of this, we're in two decks, independent, same deck, not independent, or in a way dependent. So now our formula becomes the probability of K1 times the probability of K2 given K1 has already occurred. Now we can take that formula where this easily becomes the 2, this easily becomes the 1, and this the 2. This is 4 divided by 52, and this is 48 divided by 52. Then the probability that K2 would occur given K1, meaning that you would essentially draw a probabilistic event along this path. Now we can calculate this by doing 4 over 52 multiplied times 3 over 51, and that's equal to about 0.4%. And this is the likelihood of this occurring if these two events, out of all these possible outcomes of branching, should occur going down this path alone. Additively, across all these events would equal to 1. This one's only 0.4% that you would draw two kings in a row from the same deck. Now, back to our formula. It goes that we wouldn't really need formulas at all if we could just look at a branching diagram for everything. Now, consider that this is very, very, very simple in terms of probability. We're doing two events that are not independent, but occur only out of 52 cards and are only in one deck, 4 kings. And the probability of outcome is equal at the beginning. But most events aren't like that. And you can't just look at a diagram and then figure out event to event what the likelihood would be. Now, for our own benefit, we'll want to move some things around in this formula using simple algebra. So I'm going to change this back to 1, this back to 2, and this back to 1. So if I were to simply take this aspect of the formula and move it to the right and then divide by probability of K1, we could then calculate the probability of this occurring, i.e. the probability that K2 will occur given that K1 has already occurred using the outcome of this number. So let's just go through and calculate that really quickly. 4 over 52 times 3 over 51 over 4 over 52. And that's equal to 0.058. Now, 3 divided by 51 is equal to 0.058. So we did something right. This should all start to look familiar because these are the building blocks for Bayes' theorem. Well, why do we need Bayes' theorem? I touched on this before, but it allows us to convert trees like this, which let's just go through and count the different outcomes that can occur, considering that this probability is 1 that you're doing the event at all, and we'll forget that one. King, no king, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we'd have 12 possible outcomes in this tree alone, right here. Consider that we did it the other direction. Normally it would matter the direction, but this one we're drawing kings twice, so it's not relevant which order they're in, and the probabilities will be the same. But consider that a king is drawn the first time, and then maybe a jack is drawn the second time. The order of this formula here, the probability of K2 given K1 as opposed to the probability of K1 given K2, are completely different and will have different outcomes that will equate to kind of a flipping of this diagram from these 12 possible answers to gain and another 12 possible answers to gain, where this in the formula is just switched to probability of K1 given K2. And this is what Bayes' formula allows us to do. It allows us to turn a few independent values where these aren't dependent on the outcome of the other. If we can gather these independent values, we can then calculate every possible outcome using variations and algebraic manipulations of this. Now, the coolest part about Bayes' theorem is that this doesn't end with two events, and it certainly doesn't end with two events that are the same. You could condition event after event after event, and Bayes will give you, given about 1/8 of the number of independent values that you can plug in anywhere along this tree, and then get the probabilistic outcome of events for, in this instance, 24 different outcomes off of those few events. I could go on and on. I could. I won't. However, there's plenty more in the homework. But if you should need more help, don't forget about office hours.